right? Now let's consider a little bit more difficult example, which would require some algebra to do it. I will set it up as a problem for you to perform all the mathematics explicitly. So this is a water molecule, and to simplify our consideration of a water molecule, we can limit ourselves by its 2D model. So in that case, we will have only rotation in that direction or in the opposite direction. Yeah, so just a single rotation. In the 3D case, of course, we will have two others, but it's clear that in order to build vibrational model for this system, it's sufficient to use a 2D consideration. Then, and we will have, in the case of 2D, two translational invariance conditions. So along the x-axis and along the y-axis, right? So we shall first write these two conditions, translational invariance, and next we shall write rotational invariance. And rotational invariance requires that we take a vector product of the actual position of each atom and its displacement and sum over all atoms. So here we need to specify equilibrium positions of each atom. So atoms 1 and 3 would have these equilibrium positions and this. And the equilibrium position of atom 2 is 0, so that term will not contribute. And the displacements are given by the x1, y1, and 0 for the z, x3, y3, and 0 for atom 3 again. So you can easily calculate this vector product, and the final expression you will obtain is written here, where this angle alpha is this one between the OH bond and the symmetry axis of the molecule. So we have three conditions, linear conditions, which relate coordinates x and y of our three atoms together. So these conditions, these two and that one. So we have three conditions, so that means we have to subtract from the total number of degrees of freedom of our molecule 3 degrees of freedom. So how many degrees of freedom we have here? We have a two-dimensional case. Each atom contributes 2 degrees of freedom, 6 altogether, minus these 3, so we expect just 3 vibrations overall for this molecule. And of course, when we consider three-dimensional case, that would be still the same. In the three-dimensional case, we will have 9 degrees of freedom. There will be 3 translations and 3 rotations to eliminate, so 6 altogether. So 9 minus 6 will be still these 3. So therefore, considering a two-dimensional model is entirely sufficient in that case, because the molecule is planar. Of course, if the molecule was not planar, we will have to consider a three-dimensional case, but that would be practically the same type of consideration, maybe not to be performed entirely analytically, as you will see is the case here. We can do everything analytically. Okay, right. So we need to define 3 generalized coordinates for this molecule. And the idea is that any other coordinate of the molecule can be of any atom of this molecule can be expressed entirely via this set of 3 coordinates, exactly in the same way as we related the 3 coordinates of our linear molecule via these 2 coordinates in a unique way. So a good choice here is, you can consider various choices here, but this seems to be a good one. So we have x1 plus x3, x1 minus x3, and y1 plus y3. And you can easily see, using these 3 conditions, that all coordinates, all 6 coordinates of our atoms can be expressed uniquely by these 3 q coordinates, and these are given here. The next step of our consideration is to consider potential energy of this molecule and kinetic energy of this molecule, and derive them via these 3 coordinates only. Okay, we know how the old coordinates are related to the new coordinates q via this, so we simply need to perform some mathematical treatment here. So we shall assume that the potential energy of our molecule consists of the following three terms. So this would remind you about our force field we discussed before. The first two terms correspond to elastic terms along these OH bonds. So these DL1, 2, DL3, 2 are changes of the bond length here. And this term corresponds to the change of the angle here, all right, with some elastic constants which I introduce here, the potential energy. So what we need to do is to get the elongations, these two, and the change of the angle d alpha, if we have all these six coordinates, these ones, and these ones, being non-zero. So you will have a problem for that to solve, but I will just give you the final result that these elongations, DL12 and DL32, considering this displacement being very small, remember we are within the harmonic picture, they're given by these two expressions, and the change of the angle alpha is given here. Okay, so it's a good exercise to actually try to show this. And once we know these elongations and the change of the angle alpha, we can substitute them in the potential energy expression, rearrange this, and this is what you will get. You will get a term for QA, which is separate, and these three terms, which connect together QS1 and QS2 coordinates. So these are not separate. Similarly, we can consider kinetic energy. The kinetic energy is given, of course, by this expression where R1, R2, and R3 are vectors. So you will have R1 dot is, of course, squared is x1 dot square plus y1 dot square, and so on for others. Again, you substitute here all our expressions for the q coordinates, and you will derive at that expression here. And in this case, you see that all three coordinates come separately. The equations of motion are easily constructed by using Lagrangian formalism. And I advise you to read about this if you haven't done this before, but there is also a problem I put together to illustrate to you that formalism basically is equivalent to solving Newtonian equations of motion, but it's a bit more general because it allows you to use, instead of just Cartesian coordinates of atoms, any coordinates. And this is the case here because these are not Cartesian coordinates of our atoms. These are some generalized coordinates. And therefore, this Lagrangian formalism is quite appropriate in our case. Okay, so we set up these equations, and if we do so, you will discover immediately that because QA coordinate, this is potential energy for the QA coordinate, this is kinetic energy for the QA coordinate, and we sum them together, they're not mixed up with the other two coordinates, so this part of the Hamiltonian is just completely separate, and we can do precisely what we did for the linear molecule when we considered this kind of Hamiltonian by interpreting the term in front of q dot square, this one, as the 1 over 2m, where m would be the mass of effective mass of that oscillation. And that term here, the prefactor to qa square, we can then interpret as elastic constant divided by 2. And therefore, you can immediately find the square of the vibrational frequency, which is this effective elastic constant divided by effective mass. So this is the vibrational frequency associated with the normal coordinate qa only. And you can easily find how atoms of the molecule vibrate according to this vibrational coordinate. So do precisely the same trick as we did for the linear molecule. We set two other coordinates equal to 0. Then we return to these expressions and see how atomic positions change, or atomic displacement change, if QS1 and QS2 are all equal to 0 and we have only QA left. QA is changing harmonically, so we can imagine how the atoms move. And you will find that x1 is equal to x3, y1 is equal to minus y3, x2 is proportional to minus x1, but there is a mass factor to it, and y2 is equal to 0, which means that atom 1 moves somewhat diagonally here, atom 3 moves diagonally but towards the oxygen, while the atom 1 moves away from the oxygen, or other way around, and atom 2 at the same time moves along the x direction by a little amount because it's much heavier. So this was about QA coordinate. Now let's consider QS1 and QS2. These are entangled together. So these two coordinates are mixed up, and therefore we need to somehow solve this problem by looking at the Lagrangian equations of motion. So we write them with the coordinate q being either QS1 or QS2. We will arrive at two differential equations in that case, which can both be written in this matrix form. And all the details will be set up as a problem for you, as I mentioned before. And this matrix differential equation can be solved by assuming this exponential trial solution with a constant vector y and this oscillatory exponential term with some unknown frequency omega. And by substituting this trial solution into these equations, we shall arrive at the eigenvector eigenvalue problem for this 2 by 2 matrix A, this matrix here, by solving which we shall obtain two eigenvectors and two frequencies corresponding to them. And for the frequencies themselves, we shall obtain this fourth order algebraic equation, which is quadratic with respect to the frequency omega square, which will give us two solutions. Frequencies are positive, so we'll have two values for the omega square, two frequencies, as we expect in this case, because we consider two mixed up coordinates QS1 and QS2, which should give rise to two separate normal modes. And we will get from this equation the frequencies of these normal modes. When we look at the eigenvectors, of course, this will be for each normal mode proportional to each other, these two coordinates. And once we know how they are proportional, and the fact that QA is equal to 0, if we would like to investigate how atoms move for each of the normal modes, we will find from our previous relationships given here, in which we set QA is equal to 0, we will find how these coordinates depend on this QS1 and QS2. But as I said, these are proportional actually, and you will see how they are proportional when we will solve this problem in detail. You will find that for each of the modes, the coordinates, all 6 of them, are related directly via one coordinate only, and then you will see how they change in time. And this is what we will find. You will find that one vibrational mode, one normal mode, corresponds to these hydrogen atoms moving in or out synchronously, and the oxygen is not moving. And another mode in which hydrogen atoms move synchronously away from the oxygen or to the oxygen atom. At the same time, the oxygen atom, as being much heavier, moves in the opposite direction by a little amount along the y-axis. So these are 3 modes we find for the water molecule, and given the explicit expression for the potential energy, you should be able to actually calculate these modes, and this can be actually done. So here I show you a model for the water molecule, which was obtained based on experimental data, I believe. But similarly, you can do you can find all the elastic constants in this model here by using ab initio calculations on the water molecule, and just stretching atoms a little bit, moving them around a little bit, and fitting the constants to the change of the total energy. You see that these two terms correspond to the energy expression we have already used, but there are two others which were added with rather small constants. You can see that these two are really small as compared to these two given here. But this will give a better precision for the energy. So all the data are here, and using that data and doing your calculation, you will be able to find the vibrational frequencies of the water molecule.